Thank you, Marcus. So my name is Barbara Rothen. I'm from the Adolf Merkel Institute in Fribourg. I'm missing my co-chair, which is Frederick. I don't know him personally, but I suggest that I will just start and then hand over the discussion part to him. So he's not here? Okay, so I will go on. So thanks a lot for giving me the task to co-chair this session. It was a great start already with fantastic talks. And I would like, so maybe not as an older person, but as a more experienced person, also like to really acknowledge that the former speakers also showed key papers from the last century. So really, it's important that if you start with a new project, that you really go back also in the literature. So usually if I have a new PhD student and they start enthusiastically with research, with experiments, and after 1 or 1.5 years, if I force them to write down something, they realize, oh, something has already been done. So really read, do a lot of literature research, go back to original papers and do not only read reviews. So very brief advice. So the next session will be about bio-inspired material design. The first speaker is Joanna Aizenberg. She has a PhD in structural biology and is currently professor of chemistry and chemical biology at Harvard University. And the second speaker is Professor André Studart. He did a PhD in material science and engineering and is now a professor in complex materials at the ETH in Zurich. So it's great to have both of you here because we collaborate in the National Center of Competence in Research, Bioinspired Stimuli Responsive Materials, some responsibility. Joanna is actually in the scientific advisory board, so usually she sits here and she's looking at my talks, and now we do it differently. So please, Joanna, you start.
Thank you so much. Let's try to do it fast and at least to leave a lot of space for questions. Things that I wanted to cover, multiple things, especially taking into account the talks that we have already heard today. And for example, the previous one, the half of this was on emphasis on mechanics, the second half an emphasis on chemistry. And what Andrea and I would like to say is that there is even more, or at least a lot of interesting things are happening when we think about structure, when we think about geometry. There is additional properties, better properties that one can consider very relevant to biology, very relevant to biological materials, and certainly relevant to interfaces. So the first part of our joint presentation would be on looking at the importance of structure on the 2D surfaces, and then looking in the bulk. In particular, what I will try to do, and it doesn't matter how much I will cover, because apparently we're tight on time, I will, instead of generally talking about biological inspiration, I'll focus it on plants inspired only. I'll talk a little bit about lotus leaf, then pitcher plant, then Venus flytrap, and then iridescent seeds. And in particular, as I mentioned, thinking about bio-inspired interfaces. So let's begin with chapter 1, thinking about it as pitcher plant, as lotus leaf inspiration. So what is happening at the moment where, in addition to chemistry, we add structure? So if we just talk about chemistry, and in particular whether the surface is hydrophilic or hydrophobic, and of course that can be done purely with chemistry, there is a contact angle that will describe how the liquid likes the surface, and this contact angle for hydrophilic surfaces in interactions with water would be less than 90 degrees, this is how they are defined, and it would be higher than 90 degrees for hydrophobic surfaces. What is interesting is it doesn't matter what kind of chemistry you use, maximum contact angle that you can get for hydrophobic, purely hydrophobic surfaces would be about 120 degrees. And minimum angle, so for water that likes your surface, if it's a flat surface only based on chemistry, you won't get below 20 degrees. So something interesting is happening the moment, in addition to chemistry, you begin to add structure. So the same surface with exactly the same chemistry, if it is structured on the nano and micro scale, will add something to the property of the liquids interacting with this surface. And in particular, in a very simple way, one can think about now this liquid sitting instead of solid, because its interaction with solid is exactly the same as with the flat surface. But it's now sitting in a cushion of air. So it is sitting on the interface composed both of a solid and air. On air, liquids would form full sphere, which means contact angle with air is 180 degrees. So if you have a liquid on a structured hydrophobic surface, for example, then its angle would be between what it makes on a flat surface, let's say 120, and 180. So in fact, the liquid sitting on this complex substrate experiencing more air if you structure it in such a way that solid fraction is very low, and outcome of that the droplets are nearly spherical. So the function of structure then, with any chemistry, anything that it gives it hydrophobic character, is that the droplets will sit in the form of almost spherical droplets, and therefore they have the ability to roll off this surface, pick up the dirt, and in this way clear the surface. So the angles become nearly, this is the contact angle, the one that you consider for the surface, is a complex angle that is composed of solid and liquid fraction. What is interesting, this is hydrophobic surface. So lotus leaf is hydrophobic. It is super hydrophobic. Now if you would have hydrophilic surface, just the same way as hydrophobic surface being structured becomes superhydrophobic, if you have hydrophilic surface being structured, it becomes superhydrophilic, which is that water on that surface, even though it had a contact angle below 90 degrees but not zero, when it is structured, it will be nearly zero. It means that it will form a continuous film on the surface. So structure is extremely important. Probably in this particular case is dominant factor that will give you either superhydrophobic or superhydrophilic properties. So one can use that, of course, as a way to think about new materials that can change their properties, and we can build them in any way we want. But the most important thing that then if we look at the interaction of droplet of water on hydrophilic surface, of course it loves it, it spreads and stays. On hydrophobic it spreads, contracts, but it's still always in contact with the substrate. But on superhydrophobic surface, water droplets would touch the surface and being able to be repelled completely, leaving the surface without contact with the liquid at all. What it means is that there is a lot of interesting things happening in literature trying to reproduce these properties for different applications, in particular those that would be related to biological materials. There is a problem though. So what if I now compare what happens on a flat surface, and let's take bacteria as our proxy in this case, take structured hydrophobic surface, and hoping that if it's structured and structured on a length scale smaller than the size of bacteria, then the contact with these cells is reduced, so adhesion is reduced. So maybe there are less cells forming on these surfaces. But then if we take, for example, E. coli as an example, what happens then, and it's shown on this graph, is if we compare wild type, and this is the E. coli without flagella, then yes, at the beginning, if we look at the ratio of a biomass normalized by the flat surface, so it's about 80% reduction in the amount of bacteria attached to the superhydrophobic surface, structured surface, at the beginning. But then, after 2 hours or so, actually picture is changing. And picture is changing in a very unpleasant way. It's changing to this extent that the number of particles or a biovolume accumulated on the surface, and then we, in this case, talk about biofilms and bacteria, is actually significantly higher than on a flat surface. So instead of promoting an absence of adhesion, it actually promotes the adhesion on the surface. And there are multiple reasons for that. And one of the reasons is that for surface to stay superhydrophobic, it has to be hydrophobic. But biological matter in particular, not only biological matter, but in this particular case, it will be able to change the surface chemistry. With time, the chemistry of the surface to which it is attaching is changing, constantly changing contact angles and the type of wettability it creates. So the outcome of that all these crevices that were not available before now become available. So actually the surface to which bacteria can attach with time as it changes the surface chemistry is higher than on a flat surface. So the outcome of that it actually now has higher biomass accumulated on these surfaces. Now, there are other physical reasons that happens, and in particular, at least with bacteria, it uses flagella to initiate vortices in the structure. So as the flagella experiencing the interface, it actually forces, physically forces, not even chemically in this case, into the crevices, and the moment wetting occurred, it undergoes transition from superhydrophobic to highly wetting stage, and therefore wetting occurs, and now bacteria can attach any side you want, and the outcome of that is that actually you will have very well developed bacterial community on the surface, even though it's superhydrophobic to begin with. In fact, if you look at this more thoroughly, and it would be the last slide to finish the story with lotus leaf, yes, it's a wonderful inspiration, but let's not forget that it is naturally evolved to deal, first of all, only with water, not with other liquids, not with complex liquids, in particular those that we have in the body and are biologically relevant, but it also dealing with very specific range of temperatures, and it has the ability to regenerate the surface. So in fact, if you look at that and you think about the fact that if I use low surface tension liquids, and this movie playing here is showing it very well, the wings of butterflies are superhydrophobic, and when water is touching them, it repels it. But when alcohol is touching it, it actually infiltrates the structure. So it cannot handle low surface tension liquids, it cannot handle surfactants, it cannot handle any contamination or mechanical damage or high pressure, and in fact all that would change the property from this non-sticky condition to highly sticky condition, when the liquid is actually capable of interacting with the entire surface, not only with the tips of the structures, but also the entire structured interface. And if we think about physics of liquid repellency, it's not only the contact angle that describes the interaction of the liquid with the interface. Even more so, what describes this interaction is what is called contact angle hysteresis. Still not the best way to describe, but still much better than this using contact angle. If we think about inclined surfaces, or let's forget whether it's inclined or not. If we think about liquids moving on the surface, then moving droplets are not described just with the contact angle. It's described by difference between receding and advancing angle. As droplet moves, if we assume that receding and advancing angle, doesn't matter what is the value, high or low, you don't even have to go to superhydrophobic values, but if they're exactly the same, then the contact angle hysteresis is 0, which means that there is no friction that this liquid will experience on the surface, and it will slide off the surface the moment it is inclined or some force is applied for this liquid to move. So maybe, and this is what actually happens on most surfaces, including superhydrophobic, is the fact that you cannot, even if you try hard to make the surface as smooth as possible, there is always nano or even angstrom scale defects on the surface, and the nanoscale roughness, and this roughness creates pinning points for the liquid. And this roughness, it could be chemically or purely geometrically, creates a difference between the receding and advancing angle. And it means that the droplet is pinned on the surface. So maybe the idea is, instead of thinking about how to increase contact angle, as Lotus leaf is doing it, how to decrease contact angle hysteresis. So there is no friction and the droplets can move freely. Now again, nature does give us a good example. With surfaces on another plant, this is pitcher plant, that on a dry day, insects, it's a carnivorous plant, they are running around nicely on the surface, but on a wet day, this plant has a high appetite, and none of these insects can be now moved on the surface. They're trapped inside, they just slide into the stomach and digested by a plant. So what is happening here is actually what I mentioned as superhydrophilicity. So if you look on the structure of this surface, the structure is very similar. Again, all about structure. Structure is very similar to lotus leaf structure or other superhydrophobic materials. But in this case, it's not hydrophobic, it's hydrophilic. So on a dry day, these ants experience the structured surface, they run around nicely. But on a wet day, since the surface is hydrophilic and structured, it means it's superhydrophilic. So it picks up water, and now ants that have these oily feet never in contact with the solid itself. So contact angle hysteresis in this case would be determined by the interaction between oily feet and the liquid, in this case water layer. And liquid-liquid interactions, unless they have chemical interaction between them, but in this case it's oil and water, pretty much non-existent, and the outcome of that is that these surfaces are highly slippery and cannot stay on the surface. So the idea here is, let's think about materials that have the ability to create this layer of a liquid protecting a solid, in this way creating liquid-liquid interfaces that are slippery and therefore non-sticky. It's actually not only in the pitcher plant, it's everywhere in our bodies, it's in our stomach, it's in our eyes. There is always a mucus layer or some liquid layer that protects the solid interface. So if we think about it generally, we can think about using a surface, roughened surface, and you can roughen it in any way you want, and you will see that feature sizes are not that important, but what is important is that it would have chemistry that has high affinity to a liquid that it will trap. In nature, it's water, but it doesn't have to be water, depends how you functionalize your roughened surface. And in this way, if you do it properly and look at every energy of different interfaces, how to functionalize the surface, which liquid you use as your, let's call it lubricant, then any liquid on top would never be attached to the interface. It would be freely moving outside, and really everything will then slip. And this approach is called slippery liquid-infused porous surfaces. Now, as a platform technology, you can change type of liquids that you use depending on application. You can change type of solids that you use to create your designer interface to repel anything you want. And indeed, you can repel pretty much everything. What is important is that now liquid is your functional part, and liquids are reconfigurable. And the fact that liquids are reconfigurable, it means that you have as add-on feature self-healing. Not only it repels stuff, but it actually has the ability to self-heal the moment you have damage. There are other things you can imagine, that knowing that feature sizes could be at the range of sub-wavelengths of light that is used, it can have anti-reflective properties. So not only that you can create non-fouling surface, but it could be fully transparent. Or you can create surfaces where you have patterned regions of structured surface, patterned regions of non-structured surface. Therefore, there would be regions where liquids would move fast and where it would move slow. You can also create materials that are mechanically stretchable so that the surfaces can change its structure from the ones that have slippery properties to the one where they have sticky properties. And in this example just shows how that can be done mechanically. As you stretch it, you change porosity, and the outcome of that is that the liquid either sticks and you have this on-off switch of liquids to go on the surface, to stick to the surface. But even when it sticks, it doesn't leave behind any dirt or anything else. So the outcome of that is that you can make materials, different materials that can deal with marine fouling. You can have lenses that don't accumulate any dirt, or you can have surfaces that have no fouling on them, and you can have many more things. And I will probably talk in my lecture on Thursday on medical applications of these surfaces. What I do want to do now is skip this material, because this is what I'm likely be doing later. But now, let's talk about yet another third lesson, and again, surfaces and again, structures. And in this case, I want to put a whole range of seemingly unrelated biological materials, but we're mostly talking about plants, and we can think about wheat awns or Venus flytrap, and they're seemingly unrelated. But what I want to say here, that if we think about Venus flytrap that has the ability to trap flies, or we think about wheat awns that have the ability to self-seed themselves into the ground, and the way they do it is by changing the angle between high aspect ratio structures. But in fact, if you go further, there is always presence of these high aspect ratio hairy surfaces. So there's something interesting if you have these surface cilia, in some cases it's cilia, but it doesn't have to be, and if it has the ability to move or respond to environment, it could give you reconfigurable moving hairy surfaces. What can we do with that? What can it give us as an idea for new materials? So let's say we will create our synthetic analog of hairy surface. This example is in particular silicon. There is nothing living about silicon, but at least it has some hairs on them. These are more or less in the size of cilia in biological literature. Can do nothing this way, but we can play with chemistry, and we know that chemistry can swell if we take hydrogels, or contract in response to different environmental stimuli. So we can now combine them together, hairy surfaces with gels, and create synthetic hair. And these now can actually move in response to stimuli. They can stand up, lie down. You can make it more interesting. You can add particles inside that and locally heat them up. In this case, this is particles of gold. And I can now remotely actuate these surfaces. And in this way, I can create surfaces that adaptively change their structure in response to environment. You can use different types of these materials, and these surfaces begin to move as you need in response to temperature, pH, humidity, you name it. The outcome of that is that you can create materials that have this ability to move, ability to change its structure, maybe to use it to change fate of cells. Not only that you have structured surfaces that are important, but you can now mechanically actuate them so that cells experience these forces, and instead of uniform spreading, would have directional spreading. Or, and this would be the, the last one I will show, you can use it as a way of capturing molecules and bringing them to another layer and using it as a system for biomolecular detection and sorting. Again, as a system that has surface properties where hairy materials respond to environment, capture molecules, contract due to change of the environment, and bring it to another layer. There's many other things that you can do with that. I would actually not go into that. And let me, instead of going a lot through this, just show one slide as a fourth type of things that we probably want to consider is structural color. Again, structure that gives you interesting property, and how one can use it as an interesting detection mechanism that more and more we now use to try to think about materials, where materials and liquids, and type of information detection where it can be sensitive to different moieties in the liquid, and it will selectively change color depending what kind of liquid you introduce. So in this way, I've shown 4 to different extent, but all 4 examples that I was showing were getting its property from structure. Of course, chemistry is one element of that. Of course, mechanical properties is another element, but it is structure that is most important, and it's structure that gave emergence of otherwise impossible to achieve properties in other systems. And with that, the only thing that I want to add, and in this way to give a podium to André, is even more interesting things happens with structure if we suddenly explore 3D. If not only surfaces are involved, but now we are going into 3D structures and what can be done at the moment when we think about adding bulk to these materials and how that would affect the properties and functions. So.
All right. Thank you very much for the chance to be here and contribute to this lecture. Thank you so much, Joanna, for introducing the idea that structure really matters on 2D surfaces. I want to extend this concept to the bulk. And as opposed to Joanna, I will pick one single material and I will discuss why structure matters for this material, and especially why the interface, the mechanical interface of this material is really what dictates its design and its mechanical properties. So you're probably familiar with this. If you're not, it's fun to look at a seashell, because that's the material we'll be talking about. All right, and we will be talking about primarily, And I will focus on mechanical properties. And I want to highlight at the beginning something that we're very familiar with, that some materials are just very brittle. And that is the problem that I would like to discuss with you today. So if you look at this experiment, you probably can predict what's going to happen. We're very familiar with materials that are very brittle. And this happens when you have a high concentration of inorganic phase, more specifically inorganic non-metallic. So ceramic materials are very brittle, and this is what these materials like seashells, like these little biological armor of these shrimps, and also our bones, our teeth are very good at solving the brittleness problem. And that is the problem that we'll be talking about today. So what's really amazing about how they solve this is obviously through structure. And this is a nice way to show how they solve the problem in a more quantitative way. We are looking at the Nashby diagram, which shows the strength or the toughness of a material as a function of the elastic modulus for a number of different biological materials. And what I would like to highlight here is that the seashell itself has 95% of calcium carbonate, which should be down here in the diagram. So it's a fairly poor material in terms of mechanical properties. But through structuring, the organism is able to increase the toughness of these materials by orders of magnitude, even if it's made out of 95% of calcium carbonate. So how does it do that? So today I'd like to tell you what are at least some of the design principles behind this amazing effect of structuring in a bulk material. And then I'll tell you how we've been trying to mimic this effect. And here we don't want to mimic the seashell. We want to mimic the design principles of the seashell, because it's not always that we want calcium carbonate in our chemistry. We might want to have stronger materials or perhaps similar materials, but which are more resorbable or less resorbable in the body. All right, let's start with the design principles. So if you look more carefully at this seashell that is passing around, first thing you will see at a macroscopic scale is that there are these larger layers in the hundreds of micrometers scale. So this layer here is the nacre layer that we will be talking about. And this is generated during summer. Then, during winter, the organism stops producing nacre and produces instead an organic layer, which is called the meso-organic layer. Now, if we zoom in the nacre layer itself, and you're probably familiar with this, you find this beautiful brick and mortar structure. So these are platelets of calcium carbonate, more specifically aragonite, which are organized in this beautiful way in a brick and mortar architecture. Now, if we zoom in at the interface between these platelets, you'll find something really interesting. You'll find that some of the platelets are connected through what we call mineral bridges. And this has to do with the way the organism builds the material. And some of these are really connections from one platelet to the other, and some are just asperities. Now, if we would look into what's in between these platelets, so these remaining 5%, this is a polymer phase, which is very soft and slippery. So what we will be focused mostly is in these two intermediate length scales here. So the length scales of the individual platelets and of these mineral bridges. All right, so what happens if now we are trying to break this material? If a crack starts propagating through the structure, and the structure is designed in such a way that the platelets are always aligned parallel to the surface of the shell. So if you try to bend it, you would have a crack going this way, perpendicular to the direction of the platelets. And what you find is that this crack has a very hard time to go through the material. And that is because it is always deflected whenever it finds a platelet. So this is a very important concept here, that instead of propagating through and creating very flat surfaces, which would happen if the platelets are breaking, we rather have the platelets remaining intact, for most of them at least, remaining intact, and then the crack always needing to deflect at this interface, and that leads to this typical zigzag pattern and a lot of toughening mechanisms, some of which are listed here. Crack deflection, friction of the platelet as you try to pull it out outside of this surrounding material, delamination between the platelet and this organic phase, which we call matrix here, plastic deformation, and so on. But all these require that the platelets do not break. So the platelets should carry as much load as possible, but should not break. They should carry a lot of load because they are the stiff phase, and there's nothing that connects the individual platelets, or what connects the individual platelets to the outside world is this 5% organic phase in between, right? So they should carry as much load as possible, but should not break. And that brings us to these different possible fracture modes, and this is classical composites. It's not something specific to this material, but in general, you do have these two situations that, in one situation, the stresses that the platelets feel, and these can be rods, fibers, and so on, are just too high, lead to their fracture, and you have they carry a lot of load, but the crack just goes through the material, as opposed to the situation which I just described of pull-out, where you have to pull out the platelet from the surrounding in order to keep propagating your crack. And what we're really interested in is that to come up with a design where we can carry as much load as possible by this platelet, but we don't break them. We are still in the pull-out regime. So how can we do that? Now I'll do a very difficult experiment. Now all what we will think about is this little platelet in the middle of nacre, right? So we consider all the surrounding platelets as a continuum, and we're just looking at one single platelet, and we want to ask ourselves, how are stresses transmitted to this platelet? And here I will just use a chalk rod, just as an approximation for the platelet. And what I'll try to do is to break this piece of chalk, by tension, right? I can't do this. So the trick is that you shouldn't bend it, because of course that's very easy. The idea is that you pull on it. It's very hard, right? But now, what happens if I have this piece of chalk? Marcus, can you break it for me? Tension, huh? No bending. Just tension. Oh, I see bending.
It's the age.
It's the age, okay. Very tough, right? Very difficult. Why is that? It's as simple as you can think. Why is it? You can't really grab it, right? You can't grab it. The area that you have available here to pull on it is just too small. I just can't transmit enough force to this chalk to break. And that is the very, very simple idea. The first one that happens at the length scale of the platelet. It's just an area argument. So if you look at this piece of chalk, what I'm applying is this force with my hands, which are basically a shear force, over an area which is shown here in blue. So this is the envelope area of this chalk. So this is all this area that I'm touching now. And this force is being balanced by a tensile force inside the rod. But what's different here is that this force inside the rod is applied to another area. It's applied, if you're really breaking under tension, it's applied through the cross-section, right? So the basic idea here is really just playing around with the areas. So if you do this force balance, and you say the force inside, this tensile force, should be equal to the shear forces on the surface, now you can take into account these different areas, and that will bring in a stress, tensile stress, and a shear stress. So a stress is force divided by area, so that's how you come to this equation. If you work on it a little more, you put in the surface area in blue, the cross-sectional area in red, you come up to this, and this leads to this very, very, very simple relation of the stress, tensile stresses that your rod feels, for one given applied shear stress that I'm applying with my hands, and these are related with geometry, the length divided by the diameter of the rod, right? And this is the aspect ratio, the length divided by how thin it is. So it's a measure of how elongated it is. So it's very easy to predict. If you have something very elongated, high aspect ratio, you will develop very high tensile stresses inside the material as you apply a given shear stress, right? Very simple. All right, so then you can assume you cannot apply a shear stress higher than a certain maximum value, and this has to do with how greasy maybe my hands are, and this leads to this very simple equation. So now I told you we should make sure these platelets or rods should carry as much load as possible without breaking. What does that mean? That means, and that is because if the tensile stress inside the material is higher than the fracture strength of our rod, we will break it just as in my experiment. Instead, if these tensile stresses are lower than the fracture strength, we are in the desired pull-out mode, right? Very simple. Now, the second experiment, and now it's a thought experiment because this is a little bit harder to do, is the following. Before I tell you the experiment, I just want to bring one very basic concept about the mechanics of brittle materials. And that is the dependence of the strength of this brittle material on the size of the defects inside these materials. What does that mean? That means that, let's assume we have this little plate as our brittle material. If we put a defect in the middle of size C, this is just a hole. Typically it's more of an elliptical shape. Just imagine now pulling on this material to try to break it. What happens is that all the stress lines that come at this region basically cannot transmit their forces to the other end, right? So everything has to come around the defect, which means you will have a stress concentration in this area, which is not a problem for a metal, which will locally deform plastically through motion of dislocations, but it's a big problem to a ceramic material which cannot deform plastically. And that is the reason why the strength of a brittle material is never a material property. It has to consider also the size of defects, right? And what's even more interesting is that people figured out a very simple correlation between the fracture strength of such a brittle material and the size of its defects. So it scales with 1 over the square root of the defect size. So now we go for our experiment. I have this big piece of chalk and I have a small one. Which relation holds true? First, the strength of this big one is the same as the small one. The large one is stronger, or the large one is weaker. What do you think? Who votes for 1? For 2? For 3? Yes! So why is that? The strength of the large one will be smaller because the size of the defect, the critical defect, scales with the size of your platelet. So we can do an approximation and say the size of your defect should be proportional to the size of your platelet or your rod. So this allows us to use this very simple relation also to predict the dependence of the strength of our platelet on its thickness, which is quite interesting. It means that the thinner you would make these platelets, the stronger they are. All right, so what have we learned so far in terms of design? First, we want to make sure that we are in pull-out mode, but we also want that the platelets carry a lot of load. And so we learned this very simple relation, which shows how the tensile strength, stress on the platelets correlate with the shear stresses that is being applied by this polymer matrix all around. And this correlates to this simple geometrical factor, which is the aspect ratio of our platelets. We also learned that it's good to be small, right? The smaller you are, the stronger are your platelets. And so, as I told you, the stress on the chalk should be maximized, but it should be lower than the fracture strength of our rods, right? So what does that mean? That means that if we take this simple first equation and we say, what is this critical condition at which you will eventually break the platelets? That is when sigma reaches sigma f, right? So I just replace the fracture strength in this equation and we get then this critical condition, which predicts what is this critical aspect ratio above which the platelets will break, below which they will not break, and we will stay in the pull-out mode of fracture, right? Very simple relation. So if we now start talking about an aspect ratio, length over dimensions, we get this very simple relation. If we now add in for the fracture strength this simple prediction, its dependence on the size. So I'm just taking this equation, plugging it here, and then we get this simple relation, which predicts that the critical aspect ratio should scale with 1 over the shear strength and the thickness, square root of the thickness of our platelets. Right? Very simple, just the force balance and this behavior for brittle materials. And now we can take this very simple relation and plot the critical aspect ratio, which you see here, as a function of the platelet thickness, which you see here, 4 different shear strengths, right? These are these lines, with a slope of, in a log-log plot, minus 1/2. And so if you do that, and we don't really know what the shear strength is, if we do that, we can get these different lines. And what's really interesting now is to look into different seashells with different platelet thickness and see where they would fall in that plot. And this is what my colleague Ralf Spolenak did a while ago. So he took all these different seashells, looked at the microstructures, and interestingly enough, they have all different thickness of the platelets, and added in the plot. And what you see is that indeed, there seems to be this correlation that the thinner the platelets are, the higher is their aspect ratio, indicating that indeed this seems to be a design principle of the seashells. All right, so the other experiment and the last one is the following. In nacre, you usually have this stiff material, or you do have this calcium carbonate stiff material, and the organic matrix around it, it's not that stiff, which means it cannot really carry much load. You cannot apply a very high shear strength at this big blue interface, which means that the stress that the platelets feel are actually much lower than the fracture strength, just because the chemistries do not allow you to have something very rigid on the outside. This is an organic phase. So it's like if you would take this rod and now put grease all around it, right? To make it very slippery. And then, no matter how much I try, it will always be sleeping. I will always have a very low shear strength, shear stress being transmitted, and I can't really break it. So what would you do to fix it? Add roughness, make it rough, so that you can transmit a higher shear stress to this surface. And this is another design principle in Nacre. So this is one of the roles of these mineral bridges, at least in the beginning of the fracture process, to make them rough enough or connected to one another such that you transmit a high shear stress to the platelet. All right, so the big picture is that so far we've been looking only at these little platelets here. Now what you have to think about is the fact that they're all interconnected to one another, so it's not only roughness, but it's really a mineral bridge to all the surroundings, and this will help transmit stress that you're applying at a far distance from here into this individual platelet. And if you were to predict now the strength of this whole composite, you would now predict that the strength of the whole composite depends on just these three parameters: how much shear you're transmitting through the bridge, what is the aspect ratio of your platelets, and how many of these platelets you have. So I'm out of time, and I've only been through half of the talk, so I will go to the end, and I will wait for your questions. So just to wrap up really quickly for the design, what we really want is that to make the platelets as small as possible, so making them thin is good. And we want to design their shape, just so that they're elongated enough to carry load, but not too elongated that they would break, right? And because it is the matrix around these platelets are just too soft, we want to add mineral bridges in order to increase the shear being transmitted to the platelets. All right, so the second part is how do we translate all this to synthetic materials? And I will basically just jump to the end. Where's my computer now? Yeah. And we've developed a way to produce materials, starting off with very thin and small platelets, and create these mineral bridges. So this is the final result. What we do is the following. We buy platelets that are already very thin and very elongated. But we know that the polymer around it, just like in the seashell, is not stiff enough to transmit a lot of shear forces, so we also add mineral bridges. So the material looks like this. It's basically the size of a normal seashell. You will see that it's very shiny, and the reason for being shiny I can answer in your questions. But that's the scale that we're able to produce them. But this is still with 40% of platelets, 60% of air. So in a second step, what we do is to press on this material so that we densify and increase the volume fraction of platelets up to 95 volume percent, and then we get something like this. This is just smaller because we used a smaller mold, but this is the artificial nacre that we are creating. And this is the final plot that I want to show you, which is a result of about 10 years of research, which shows the strength of this material as a function of the fraction of mineral bridges. So the way we control the fraction of mineral bridges will come here. That is by using platelets that have a coating of titanium oxide, which will de-wet the platelet surface at high temperatures and create these little blobs in between the platelets. And the process we've developed allows us to control how many of these orange blobs exist between the platelets, and then eventually we can measure the strength of these materials. And what we find is that, at least for this preliminary data that you see here, we indeed see a linear relation between the strength of the composite and the fraction of mineral bridges that are connecting these platelets. And this is this part, and we see that under these low fractions of mineral bridges, the material indeed fails under pull-out mode. And if we go higher, you start to level off the properties and you start to see fracture of the platelets, and that is because now the stress being transmitted is just too high through this high concentration of mineral bridges. So to that, and that's when you have a fracture mode. So the very last part, what we've been able to do is, if we look back into the Ashby plot that I showed in the beginning, we started off with an alumina platelet, which is much stronger than calcium carbonate, and through structuring, we've been able to increase its properties by a factor of 3 or 4, beating basically the properties of nacre itself, so we're stronger than the seashell itself. But what's most exciting, this was the proof of concept of the design principles, what is most exciting is when you think about taking other materials which are inherently weak, like hydroxyapatite, but have very interesting properties because they are resorbable in the body, but you know they're very weak, it's very hard to make stiff implants with them. Can we structure those and increase the properties through these design criteria? So with that, I would like to finish so that there's enough time for questions. Thank you.
Thank you very much. Sometimes presentations are so pedagogic and good that you don't want to interrupt them. This was a fantastic story. My name is Fredrik Höök, and I'm the late arriving co-chair for this session. So the talks are now open for questions, and we have one up there. Am I running? You are running. Where do we see?
Thanks. Michel Müller from CSRO. My question is for Professor Aizenberg. The technology you presented is very interesting and super cool technology in general. How easily do you think you can translate it to a little bit more complex geometries, for example, open pore structures? Because everything you showed were like flat surfaces.
So your question is to which of the, I've shown a couple of them. So
To the superhydrophilic.
Superhydrophobic.
Philic.
Superhydrophilic properties, just like superhydrophobic. If it's superhydrophobic or superhydrophilic, not slippery, that's not easy to make it on a large scale because any defect would matter. So the beauty of slippery surfaces is actually, it's very easy to make it at large size because the quality of the structure, the uniformity of the structure, the porosity, how reproducibility in different areas is not that critical. As long as you produce enough surface area for the liquid, for the lubricant to be bound and stay in place. So purely superhydrophobic, superhydrophilic, they're difficult to achieve. And actually they fail in most applications.
Thanks.
Okay, while waiting for the next question from the audience, I take one from the web, and that's to you, Andrea. Can you comment on the structure of bone and how it is a perfect structure, and how its perfect structure is achieved during healing? Is that within your knowledge?
Right.
frame?
So in the case of bone, you also have obviously the challenge of addressing brittleness because you have 50% of the material being hydroxyapatite, right? And bone also uses this concept of structuring the material at different length scales in order to combine strength and toughness, being stiff at the same time being difficult to break. The mechanisms are slightly different in a way that at the smaller length scales you have collagen fibrils, which are oriented in the loading direction, in that sense similar to the seashell. And these are reinforced with hydroxyapatite platelets to make them very strong. So these fibrils, mineralized fibrils, will play the function of the mineralized platelets here, or the mineral platelets. And then you have this forming larger fibers by basically collecting many mineralized collagen fibrils into bundles. These in turn form lamellar structures around the defects in the bone. So the defects here would be these osteons, right? The places where the blood vessels are and run in this direction. But these are, just as I explained for the brittle materials, these are defects which will concentrate stress. So bone has several layers of these mineralized collagen fibrils organized in different directions because they are not 2D materials but 1D reinforcing materials. And yet the connection between these lamella is very weak. This is what is usually called the cement line. And that leads to lots of crack deflection. So you heard keywords that you also heard for the seashell. So even though the chemistry, inorganic chemistry and the organics is different, they're always similar design principles behind. And the key is to structure at very different length scales and create lots of troubles for a crack to propagate through. Yeah.
And how close are we to making something similar artificially to bone?
You asked the healing, which is even more challenging. Yeah, I forgot the healing. Yeah, so healing happens first by just throwing in organic and inorganic building blocks at that spot, but at that early phase, everything is randomized and not really in the perfect structure. And then over time, these gets reorganized through the help of cells, of course, yeah.
Fascinating. So here we have a question.
Thank you very much to both of you. I have a question about the second talk. So have you investigated the effect of the spacing between bridges on your composite strength? Is there some optimal distance to improve the strength, or are these parameters really insignificant compared to others like the platelet geometry?
Right. So the spacing will affect mostly the volume fraction of your platelets. So that's the largest effect that we see. So we can take this part which is still not heat treated like this one, and by changing the pressure that you apply during this high temperature, high pressure, you can basically manipulate the volume fraction and the distance between the platelets. So in terms of volume fractions, you would change it from 30 to 40 all the way up to 95% of your platelets. And we tend to see a linear relation with the volume fraction. So, and that is in agreement with what one would expect from a composite theory. So the key design principle here is to keep the volume fraction as high as possible. That's why it's 95%. And basically then tune how much these platelets are interconnected in order that you're at just below this critical aspect ratio. Yeah.
Thank you.
So we are closing up on lunch. There is one question there, but I think we take one for Joanna that we have here on the way, and that is, will slip be one day outcompeted by surfaces on which lubricant has been permanently immobilized?
That's a very interesting question. Depends for what, because there are a couple of things that you want to do. If we think about ability to overcome adhesion of biological matter, whether it's blood or bacteria, probably not. If we talk about longevity, and this is the issue, of course, that one has to address, probably attached lubricant would be better. However, physics of how these surfaces interact with liquid medium is completely different. The moment you attach a molecule, you have floppy lubricant, it's still sticky enough. It's not as sticky as a solid surface, not as sticky as simply a functionalized surface, but it's significantly stickier than the surface that has freely moving liquid layer. So if you want mobility, it has to be a slippery surface with unattached lubricant. If you want longevity, some of it, or at least consider ways to attach it permanently.
Thank you. We take one final question.
Hey, thanks for the brilliant talks. My question is for you, Joanna. With the slips, you overcome the problem of like having defects on a large scale. But what about stability? Because you have a liquid on your surface that has to be there for a long time if you want to have a long-lasting application. It can easily evaporate or can... So how is stability?
So as I mentioned right now, stability is an important question, but again, it depends for which application. Do you want it for years? If it's bone implant, we need to work a little bit more to make sure that it's still there. There are many medical applications, I'll show some on Thursday, where the requirement is during the procedure. For example, in bronchoscopy or any endoscopy procedure, it's 10 minutes, 15 minutes, it would work. If it's 1 week, it would work. It also depends whether it's in open air or in underwater or applications. Really, there is no one single answer. However, one interesting answer to that, and again, using another approach that biology uses a lot, is vascularization. What one can do is actually under the surface that would potentially lose the lubricant with time to have the underlying, the layer of vascular channels through which additional lubricant can be transported to the interface when it loses its functionality. So interesting thing is to think about it also as a combination of biological strategies, and vascularization in synthetic systems is also an interesting way to think about it.
Thank you. Before we thank both presenters of this talk, Marcus has promised to say a few words on the lunch event, which is a bit special.
Just very briefly, let's thank the two speakers. Excellent educational talks. Thank you.
Thank you.